So yeah, then I am gonna rewrite a bit the stuff and try to.
What was the? Have you submitted there before?
No.
I don't think they're massively late. The thing is, if we went for the IEEE option, we could kind of keep the existing structure.
Yes, but one of the they were kind of commenting on the fact that it could be short.
Methodologically.
Yeah, that we've spent a lot of time explaining what was happening. What the reviewer that wasn't convinced said that it was too cumbersome, too detailed. Only after page 17 we said, okay, this is the optimal strategy of the agent.
I see. Okay, let's get Gilles' feedback as well. But I'm open to either option, and I agree with the principle of wrapping up and not having loose ends after you graduate.
Of course, I know that it's not going to be published before I leave.
But
if we don't need to have like a strenuous
review process is not unwelcome. Yeah, sure.
Okay.
Cool. Yeah. It's like a US hotel in here.
I took
yeah, and the contrast to outside is quite impressive.
Great fun of Nicola. Yeah,
it's a good.
We made a bit of fun of Nicola yesterday because when we left the hotel, he was like, "Do you think I should take something else?" And then we not only that. When we left the Airbnb, where there was air conditioning, and then we went in the street, and it was like 40 degrees, and we were like, "Yeah, Nicola, take some stuff, like take something to put on your head. You're gonna catch a cold." But today I only took short sleeves.
Asking for €50. So I told the guy, there's no way they're paying €50. Put the meter on. It's like, no, I'm not going to put the meter on. I said, yes, but then what? Because you see foreign people, you're going to charge whatever you want. I'm not
for taxi.
They tried to rip them off yesterday. So I told and he said, I'm going to get them off the taxi now. I said, get them off the taxi. I'm not doing whatever I want. Then put the meter on. He said, no, I'll get them off the taxi. And he got them off the taxi.
And how did you go there after all? Use another taxi?
Which had the same, but they had to negotiate down the price.
But it wasn't the same taxi, but you didn't put the door.
No, the same story.
Yeah. At one point we got into 3 taxis saying, okay, once you go there, put the meter.
You have to use the app.
Ξεκάθαρα.
We didn't have the apps and...
Είναι λαγωνικό άγριο.
Lately, twice I got a different reaction because I was asking the taxi driver to get me somewhere that was relatively close. I mean, not close to walk, but it was like a 10 minutes drive. And they were mad at me for asking them because I kind of engaged them for only a 10-minute drive. And you could see that they were mad. Okay.
Yeah, but the same thing was like, I'm pretty smart, it was 40 minutes away, but then...
Still toast Psyche, ready to go?
What do you want? I mean, you have the perfect time.
Τον είδα, ναι. Okay, we will kick off the final panel of the conference. It's a great pleasure and honor to welcome Professor Sakis Meliopoulos, who's a professor at the Department of Electrical and Computer Engineering at the Georgia Institute of Technology in the US, and who will talk on the topic of From Automation to Autonomy, Infrastructure for Intelligent Protection, Control, Optimization, and Operations. Professor Meliopoulos, the floor is yours.
Thank you, Tony. It's a pleasure to be here. I was born in Greece, and I look always the opportunity to come here. And when Tony said, he invited me, I said, well, you know, I'm going to be in Athens because we have another conference next week that I'm very glad to accept. Okay? So here we are. Thank you. The title I used is because today, how many of you heard of closed loop optimal power flow. There is no such thing. And we're working on this for how many decades? I'm a little bit older from all of you, so we've been working for a long time. So I would like to discuss with you today where the technology is and how we can start doing closed loop optimization in power systems. So I'm going to give you the basic principles, a little bit about the technology, where we are, and then I will give you some examples that we're working on. And as a matter of fact, these examples are in demonstration phases, so we can actually develop the systems and make them operate. Yeah. I have a long presentation, so I'm going to be skipping some slides. Yeah. But I believe Tony is going to distribute the whole presentation, so you're going to have everything there, I guess. Yeah, so the content will be, I'm talking about the background and the motivation, a little bit about the history of automation in power systems, and the infrastructure design. There is a lot of activity in the infrastructure design, the whole thing about the smart grid and the digital system and things like that is basically describes all the activities along these areas. And I'm going to present some real-time applications and examples and some conclusions at the end. Okay. So why all of this? Okay. We have some problems in power systems. Okay. I notice here the emphasis was in markets and so on, but in order to make the markets operate, we have to have some infrastructure behind it to be able to work the markets. Okay. And the things that are happening in the power system today are multiple and generate a lot of challenges. Okay? One main thing is that we have a lot of new resources that are inverter based, okay? All the renewables and so on, and that changes the characteristics of the power system. So it is, we have the characteristics of the power system that is mainly synchronous machines based. And then now we transition into the characteristics of a system that the resources are inverter based. Okay? And presently, people are talking about the 100% transformation of the system. Okay? And many people think that this in the future, in the remote future. Well, it's not in the remote future. Yeah. Many utilities in the United States today, they started looking at how much generation they provide through inverter-based resources and how much through synchronous machines. Now in California, and they monitor this over 5-minute periods. So in California, we have now for several months, many 5-minute periods where the generation is more than 100% based on inverter-based resources. Now, how can be more than 100%? Is because they're exporting also. So during these periods, then we're dealing with a system that is inverter-based resources 100%. And the characteristics are different. We can spend a lot of time discussing this. It affects all the legacy systems we have. For example, protection and control in the power system is based on the characteristics of a synchronous machine-based system. With the inverters, now we see a lot of misoperations. We have, in the United States, there is an organization, NERC, that monitors what happens to the system. Every time there is a disturbance, we have to do a post-mortem analysis. And guess what is the number one cause of these disturbances? Protection and control, year after year. So how we deal with all of these issues? Well, it requires an increased automation and better autonomy. So we're talking also about to go beyond automation and have the systems think about themselves and operate the system by computers without the intervention of operators. So automation in any engineering system goes back to the ancient times. If we look what our 2,500 years ago, our people did here a lot of automation. And as a matter of fact, if we look what happened to the University of Alexandria, was all Greek professors and so on in almost 2,500 years ago, there were a lot of developments in automation. Okay? And let's take a close look at what is the things that were developed over the years in the power system that lead to automation. I'm going to go very fast on that. Here is the first thing that happened is that in 1970, there was the PRODAR, that was the first computer-based protection and control. Okay? And was installed in a substation in California by the name Tesla. The substation is Tesla. And then, of course, the microprocessors came about. The first computer here, there was a mini computer-based application. Okay? Then the microprocessors appeared in 1980. Okay? And then in 1984, we had the first microprocessor-based relay, and the rest of it is the developments of this. Then another important milestone is the UCA project originated with EPRI in 1986. That was basically to be able to either connect all the computers and communicate and have a central computer-based operation for the system. And then something happened in the United States. They dropped interest in that. And then the Europeans picked up on the UCA project. And out of this came the IC 6150. 6150 is a series of developments for communications and automation of protection and control. So with digital systems, the sky is the limit once we get to the, then I'm going to show you some other developments that led to the what we call today the digital system. Yeah? And then a lot of possibilities open up with this. Okay? So here is some pictures of the this particular system. The PRODAR was in the Tesla substation until a few years ago. Okay? And even if some of us were trying to make this substation a historical substation, unfortunately, PG&E, that the owner of this substation, decided just to dismantle this, and there is nothing there. You got that, okay? So, but that happened only about 7 years ago. Yeah. And then the microprocessor relays. This was developed from SEL, that's by Ed Schweitzer, who was a professor at the time that he was doing this, and now he's a multi-billionaire entrepreneur. Yeah? And he has basically about 40% of the protection and control systems in globally. Okay? And then the other important development is the protocols and the standards developed for communications between computers. Okay? And this is known as the OSI model. It has 7 layers. So any computer, and relay is a computer, I guess, can communicate with through the 7 layers. And one thing that is happening right now, when this standard was developed, nobody was worrying about cybersecurity. Now we try to redesign the system by taking into consideration cybersecurity and how we protect the communications and so on. But this is very fundamental part of these kinds of developments. Okay? And then another milestone is the introduction of GPS synchronization. Okay? When we go into the digital world and we get all the data for the system through digital systems, then we need to know what time this datum was taken. Okay? And the GPS provides this information. So every time we have a datum, we know we have a time tag that tells us what time. Because if we don't have this information, then we cannot really use this data properly, okay? For many, many reasons, okay? And then another thing happened. As a matter of fact, Georgia Tech, my group was instrumental in that. Said, well, if we look at the protection and control system, every relay has its own data acquisition system and so on. Do you know how much duplication this is in the system? Okay. We have many data acquisition embedded in every relay. Okay. So why we don't separate this? Just have a data acquisition separate from all the applications we do, whether it is protection, control, operation, optimization, and so on. And that gave rise to the merging unit. When we introduced this concept, I guess we used a different name, universal GPS synchronized meter and things like that, I guess. But when companies started developing these systems, for example, the first concept was here with the GE hard fiber. This is a data acquisition and then communicates with the rest of the world through fiber optic. Okay? And then, of course, now we have a lot of companies developing this. This is 2009 period. The project we did that we proposed this thing was basically at the start of the 21st century. Okay? It was a project in 2005. And now we have a separate data acquisition system. And then once we get the data in digital form, we can do anything we want with that. Okay? Now, also, I would like to show you this picture, which shows here a control center of some years ago, and what's happened to the control center today. Okay? In the old days, we had computers taking data and sending them to the central control center. Now, and we use the SCADA acronym to describe the process of collecting this data and so on. Today, SCADA does not exist the same way as in the old days. Basically, all the SCADA is provided by the protection and control system. Okay? And on the other hand, we kept the same process that we used for the old systems. That is, even if we use protective relays to provide the SCADA, the protective relays have capability to provide the data very fast than what the SCADA rates are. SCADA rates are in the order of 1 to few seconds. Okay? But still, we reprogram the relays to provide the data at the rates of the SCADA system. Okay? So which is underutilization of this activity. So of course, with the merging units, we can go to the actual, using the actual capabilities of these merging units in terms of providing data at very fast rates. And we have two standards there. One standard is 80 samples per cycle. So this means the rate is different for the United States and Europe because the standard is based on a cycle. And also another standard, it is 256 samples per cycle. Okay? And therefore, when we use merging units, the SCADA comes in these rates. Okay? And I would like to make some observations here. That is, if we look at all the controls, optimization, operation functions are all model-based in the power system. Whatever we do, optimal power flow, AGC, etc., is all model-based. Okay? And all control, optimization, operation functions are feedback-based. So we measure something, so it's a closed loop. Okay? As a matter of fact, the economic dispatch closed loop was established basically in the 1950s. Okay? And still using this. Okay? And all zone protection functions are independent. Protection system represents a ubiquitous system, covers 100% of the system, and gradually relays are used to provide SCADA, and there is vulnerability to hidden failures. because as any other system, protection and control system is also vulnerable to faults. Okay? And you can see here my comments. I guess many times models are error-laced. So if that's the case, then everything we're doing is going to have an error. Okay? And how we can use this new technology to verify that the models are correct, the data is correct, and so on. So that's what I'm going to spend a little bit of time talking about. So the feedback presently is based on measurements. Okay? And this means that we do not have the full state of the system when we use feedback. Okay? Now, can we go around it? Of course, we can use dynamic state estimation to compute the entire state of the system, and then we have full state feedback. That can change a lot of things. Yeah? And then the last comment is seamless integration of protection, control, and operation. It is needed because should be one system operating on the same models and things like that. And new technology enables relays to become providers of validated models and so on. Okay? So let's talk briefly about this. Okay? So here is a substation where we have the traditional legacy relays. These are, I will focus on numerical relays, even if today we have a lot of substations that are electromechanical relays and so on. So and the utilities, the power companies, basically, they keep on changing this into the new technology. So here we have numerical relays. Here we have merging units. MU stands for merging unit and so on. And typically what we do, we collect the data from the relays into the station bus and the data from the merging units into the process bus. The difference in this terminology here is that in the process bus, we have data, sample data, that is points on the waveform of the voltages, currents, temperatures, rotational speed of the generators, and so on. Okay? While the relays provide phasors, okay? And that's another issue because different manufacturers may use different algorithms for computing the phasors. So we do have that errors in the phasors as well. Okay? And of course, what we can do, we can take the data from the process bus, convert them into phasors, and populate the station bus as well. So think about this now, the new system, which we refer to this, the digital substation, it has two concentrators of data, one for sample values, the other for phasor data, and then any application can access these concentrators, get the data that needs to run the application. Okay? It's a very simple process, and notice that this can be expanded from the substation to a subsystem level, to the full systems level, and so on. Okay? So the data acquisition system is located at the breakers and power devices and so on. And then from there on, the question we can ask the following thing is that, can we utilize this kind of system so that we can enter the model into the system, and then everybody uses both the data and the model and doesn't need any intervention from operators and things like that. Okay? So that's the process that we have to go to now. Before we go there, we need to make sure that this system is fully calibrated. So this means that the data we get is valid and is accurate. Okay? And also the system does not have any faults. Okay? For example, for the data acquisition from merging units, we have to connect current transformers, voltage transformers, sensors for temperature, for speed, and so on, to the input of the merging unit. And if there is a short in that wire, we have a hidden failure, okay? A failure in the system. So can we use intelligence methods to determine if everything is okay and there is no faults and the data is calibrated? The answer is very simple. Okay? but before we get to that point, let's consider what we need to do in such a way that we can do these systems very fast and in a reliable way. So the question is, what kind of things we have to do to make the system fully automated and basically autonomous? Okay? So we need to objectify the models. Okay? So when, let's say, Vasilis generates a model for a transformer, and Professor Bournas and so generates a model of a generator and so on, can they give me a model that is the same format, in the same syntax, so I can use it? Yeah? So we have to have to define the object of a device and so on. And as a matter of fact, the industry has dealt with this problem for many, many years. They came up with the Common Information Model, for those of you who have heard about this. But the Common Information Model is not a complete standard, doesn't cover all the devices that we're dealing with in the power system. So we developed at Georgia Tech a new object which covers any device that we may encounter in the power system. Okay? And then if we have every device is an object, then we can start doing our algorithms and so on in an object-oriented way. This means that any project to develop a new optimization method and so on can be very fast and efficient. Okay? So here is the process of objectifying the model. Okay? First of all, we do have a model, and any model we get a transformer, a transmission line, an inverter, and so on. We can represent it with a set of differential, algebraic equations, and so on, delay equations, and so on. Right? So what we do, we manipulate this model to make it quadratic. So if there are any nonlinearities there, the quadratization is very simple. We have to introduce additional variables so that everything will be quadratic. Quadratic means that when I have products of different states of the model, I will allow only two at a time. Okay? Squares or x1 times x2 and so on. It's a very simple process. So the end result is that we have a quadratic model, and then if I apply any degradation method, here you see quadratic integration, but can be anything, other models. So then you generate a companion algebraic form, and because you start with a quadratic model, then the companion algebraic form is also quadratic. Okay? And this is in a specific syntax, and then any computer can recognize this and manipulate this model. So this is the idea of objectifying the model. Okay? And the way it looks is this. Now, these equations may be a little bit complicated, but they're very simple. The only thing we really need to pay attention here is that this model has to be modeled in sparsity form, because there are a lot of many zeros in these matrices that you see there. It's not as ferocious as it looks, and using sparsity methods, then you process this model very efficiently. Okay? And then, of course, this is the after the integration how it looks. And the important thing is the following: that I have what we call in object orientation virtual functions, which I can take a subset of devices in the system, forming a subsystem, and then I can manipulate these objects to generate an object that represents the entire subsystem. Okay? And this is very simple. All I have to do is use Kirchhoff's current laws and so on, and it's a very simple process. So every device in the system, every subsystem in the system is represented with this object. Okay? So that's very important. And the other problem we need to address in power systems is the following. Because of the inverters, we know that the protection and control system can misoperate many times and so on. So we've been looking in the industry, there is a lot of research activity to see how we can deal with that. Okay? That's a reality. We need to see how we can deal with that. So there is a lot of talk about adaptive protection. Okay? Also, there is a way to do new protection approaches that will be adaptive as well. Okay. Now, many adaptive protection approaches, basically they try to use the protection functions that we have today and try to manipulate the settings of these relays to make it adaptive as the system changes characteristics and so on. Okay? So that's one approach. Okay? But what we've done at Georgia Tech is to develop a new way of doing protection. And this is a very simple idea. That is, we have a lot of measurements in any protection zone. Okay? A protection zone can be one transformer, one generator, or a generator and a transformer, or basically a subsystem of the power system where we have measurements and so on. So one way to do the protection is basically to ask the question, all the measurements we make for this protection zone, are they consistent with the model of the protection zone? Okay? And that can be done very easily with dynamic state estimation. And if there is consistency between the measurements and the model of the protection zone, then we say we can assume that there is nothing wrong with the device, therefore we let it operate. Okay? And if there is a fault in the system, then we need to trip that protection zone. Okay? Of course, we need to keep in mind that if somebody attacks the relays through cyber and so on, then he can generate wrong data and then the relay can misoperate. Okay? But this is the same thing that is whether we're using this method for protection or any other protection method. If somebody attacks the data, then we have a problem. Okay? So I'm going to skip the details here. It is just the simple process, I guess. And what this offers, a lot of other things. For example, I can use the state estimation to do parameter identification of these devices. If there is a consistent error and so on, we can ask the question, maybe we have the wrong parameters for this model. Okay? And so we can include the parameters into the state estimation and get the better values for the parameter of that system. Also, we can identify hidden failures. That's a little bit more complicated, but I'm going to show you how it is done. Hidden failures, if anything that is connected to the merging units and the data acquisition, we can have a supervisory system where it looks at all the data and see whether there is a problem with that. Okay? And also, and the way it is done, okay, is shown here. That is, I have all these relays running in parallel, so I can take all the data from these relays and I can set up the state estimation for the entire substation. Yeah. And once I set up the state estimation for the entire substation, then I can ask the question, are these data consistent with the model of the entire substation? Okay. And notice that this is done without any intervention. All the settings up and the formulation and so on is fully automated because of the model objectification, and therefore I don't have to have any special attention to this. Okay? And when I run the state estimation for the substation, to identify if there is an anomaly, that's the easy part, because the state estimation gives me immediately a flag that something wrong is happening between the data and the model. Okay? Then the question is, we need to identify what is the source of this. Okay? So that's a little bit the difficult part. And through hypothesis testing, we can determine whether these discrepancies are due to an actual fault in the system, in which case we need to protect the system, whether there is a hidden failure or there is a cyber attack. And basically, we can provide also the probability of what is the event, okay? And where is the event. So that's very huge information because we can take action with this information. So that's the idea of how to do that. And then finally, once all of this is done, then we can think of the relay, the estimation-based relay, as the gatekeeper of the models. Yeah, because basically through the continuous dynamic state estimation, the relay monitors continuously the validity of the dynamic model of that component. Okay, and then it can provide it to other things. So this picture here shows that if somebody wants a filter to provide from this model the common information model, we can provide this. If somebody does a power flow, then we can take this model and reduce it to what is used for the power flow and so on. So it can provide the models in different forms for the different applications. Hopefully, in the future, we don't need to use these simplified models and so on. We can use the actual object model, I guess. So the self-calibration and end-to-end testing, that's also very for a procedure. Think about the following, that is, we take all the data, this is the power system, the emerging units generate the data, we go to the process bus where all the data is located. Doing this, the dynamic state estimation, we can see if there are calibration errors and timing errors and so on. And if that's the case, then we can use the results of the dynamic state estimation as the calibration meter to correct that. And I'm going to show you in a second how this is done. And of course, if the disturbance generates some specific time-dependent discrepancies, then it indicates hidden failure, cyber attacks, and so on. So we do the same process to identify where this is located. So here is an actual installation, I guess, that is in this particular channel, there is a magnitude error of 0.6%, 1.006. There is a phase difference of -3 degrees. That was from a merging unit that was a Siemens product, okay, and had this consistent phase shift. And then the DC offset, these meters also measure the DC, that much. And so basically that particular quantity compared to the best estimate from the state estimation has these differences. And then with the press of a button, I can generate calibration constants that will take the results from this instrumentation channel and provide the validated data. Yeah? So it's as simple as that. And then, of course, for hidden failures and cyber attacks, you see how this is from an installation somewhere in Florida, I guess, where we had we allow somebody to do an attack, and you can see what happens. I guess before attack, this is the results of the state estimation. Tells me with probability 100%. Basically, the errors, the system is calibrated to about 0.1%. Okay? And then when the attack occurs, the state estimation jumps and says there is a discrepancy. It jumps to 10. This is, don't think you're going to be able to read this. So we have the attack, and then with the hypothesis testing, basically we notice that the attacker changed the emerging unit setting from 1205 to 2405. That generates wrong data for everything that's taken from that relay. Okay? And here is another case of data attacks and so on. So the idea here is the following. That is, we have a system where the only information we provide as a user is at the merge unit. We provide information how it is connected to the physical system, what is the model of the relevant power device. If it monitors a transmission line, we provide the model of the transmission line. If it provides the transformer, and so on, and also the instrumentation channel model. Okay? And then from there on, the merging unit transmits this information to everything else, and therefore the only human entry is at the merging unit. So any other components of the system from there all the way to the control center has this information, and therefore we can do things in an autonomous way from there on all the way to the control center. Okay? And therefore, I want to make the point that all of this is possible today. It's not something we're talking about for the future. Here is some installations. This is very close to Georgia Tech. We have 3 substations implemented with this. We call this to be the digital substation. Okay? And you can see here the installation. Here you see some of the user interfaces. Here you see visualizations of the results of the state estimation and so on. And you can see here the merging units installed. And so as a matter of fact, with this system, I don't have to have a big control house for the substation. A small control house can house all of this. Okay? So it is also an issue of volume, I guess. And we have now another major project sponsored by the Department of Energy, CITO. CITO is the part of the Department of Energy that focuses in solving problems when we install more and more PV systems integrated with the power system. And because most of this is happening in distribution circuits, then we transfer all of this that I talked about into the distribution system. Okay? And so let's get to the applications of this. Okay? So we can talk about optimization, network reconfiguration, intrusion detection, inertia meter, and so on. So let me go briefly through some of this. Let's start, first of all, talk about optimization with full state feedback, because the state estimation provides the full state of the system. Notice it is based on protection, and protection is ubiquitous, covers 100% of the system, so we get 100% of the system, the validated model, so on. Okay? And here is, we're working with a utility in New York. You see here the state of New York. There is a major substation here in the control center for the New York Power Authority. I'm showing only a few lines here. I'm showing this substation because it has a universal power flow controller. Okay? And this controls both the voltage and also the power flow on the system. This system is, this part of the system is 765, the highest voltage in the United States. And this part of the system is 345. So pretty much a lot of power goes through there. And as a matter of fact, today, that was the main corridor for buying power from Canada to the United States. As you know, Canada has a lot of hydro north of there, and there is a lot of inexpensive electric energy from there. And also now we built a DC transmission line that goes through the Massachusetts area and so on. And then of course we have to coordinate the operation of the DC line with this main corridor of power, and therefore the controller is needed. And here you see the approach. We have the system, we have a full state estimation, and then Autonomous will generate the optimal power flow and solve the optimal power flow. You see the results here, that is, we controlling the voltages and so on. In a system like this, controlling the voltage is the most important thing because of Ferranti effect. Anything that happens to the system, that is, let's say we're losing a reactor for the compensation and so on, the voltage can go to very high values, and therefore we need to control it in real time and so on. So you see here the results. So what I would like to talk about here, I'm going to go very briefly here. because we looked at, this is a closed loop optimal power flow. Okay? And of course, we have to have efficiency and so on. So what we're doing is utilizing these quadratic objects of the system, we can formulate the optimal power flow as a quadratic problem. That is, both the objective function and the constraints are all quadratic. Now, this is not different from what we're doing in any other optimal power flow, except the equations are quadratic. And so you see the constraints, again, quadratic. We can add anything we want in terms of constraints. Now, as you know, in the last 2-3 decades, there is a lot of activity in speeding up optimal power flows. And one way to do this is to convexify the optimal power flow. And typically what we do for convexification, we change in the problem a little bit because the actual problem is not convex. Okay? And the reason we do this is because there are many solvers, convex solvers, that we can get the solution very fast. Okay? Now, what we've done here, we ask the question, okay, how we can do the convexification by making the smallest change in the model. Okay? So when you have a quadratic model, that's easy. Okay? So for example, I can ask the question, because it is a quadratic optimal power flow, then the Hessian, it is a constant matrix. Okay? And therefore I can ask the question, can I quantify this? Of course, if the Hessian is positive semi-definite, then I know it is a convex system with certain other caveats and so on. We don't have time to discuss this. And then I ask the question, what is the minimum change I can do to the Hessian in such a way it is positive semi-definite? Okay? So I solve a very simple minimization problem. So this means that I will make the smallest change in the model. Okay? And the solution of this is very simple. I have an example here. I'm not going to go through the example. You can study it after you get the report. Yeah, time is running short, I guess, here. So we have the quadratic optimal power flow. So we transform to make the Hessian symmetric. That's a very simple process. I take the average of the Hessian, the Hessian transpose, that's the symmetrization, there's no change in the model. And then I make the minimal additions to the Hessian to make it positive semi-definite. Okay? And the way it looks here is basically, there is some other caveats to do this. We don't have time to discuss all of this. It is shown here. So we have a convex quadratic optimal power flow. Okay? And then the solution is basically, we get the solution for the convex problem. And then we say, okay, this solution is for a modified system. So I want to go and get the optimal for the full system. So what we do in this case, we use a successive linear programming to get the solution for the whole system, for the full system, starting from the solution of the convex problem. Okay? And here is an example for the 4-bar system, because that's easy to see what's happening. And here is how it behaves. That is basically, I get the optimal solution for the convexified problem very easily, and then apply the successive linear programming, and notice that 2-3 iterations, I get to the solution. Okay? That's a big advantage and increases the efficiency. Now, this is a 4-bar system, but basically we participated in the Go competition. The Go competition was a program from the Department of Energy to compete on fast optimal power flow solutions. So here is from the model 173, that was a 173 bar system. Notice the same behavior. We get the optimal solution of the convexified problem easily, and then 1, 2, 3, 4 iterations, we got to the solution of the successive linear programming. Okay? And in this competition, we had many systems up to 7,000 buses and so on. So the same behavior. Okay? You get them into the solution and then a few successes. Now, another important thing is that, let's see how much time we have. Yeah, I think we're doing still all right. Okay.
Depends how many questions you want to get.
This is a very important problem for active distribution systems. Okay? An active distribution system is one that has a lot of distributed resources. Okay? So we have feeders now in certain parts of the US and so on that have 4,000 or 5,000 houses with rooftop photovoltaics, utility-size photovoltaics, wind and so on connected to the system. And for these systems, it is the optimization. It's very important. It pays off a lot because in distribution systems, we have a lot of losses as compared to transmission systems and so on. And then optimization basically makes a big, big difference. Okay? We have a network topology optimization. I'm going to skip this slide. And as a matter of fact, here I would like to acknowledge Noli's father, where he did this paper back in 87, okay, where we started talking about reconfiguration of systems and pay attention to the discussion we have with the utilities. Basically, in transmission system reconfiguration, the gains are minimal. That's what the industry thinks, okay, which is probably right. And then they also asking the wear and tear of the breakers by doing reconfiguration on a transmission system may offset the gains that we have. Yeah? However, for distribution systems makes a big difference, and everybody does that. Yeah? We have what we need to do in an active distribution system, both the optimal reconfiguration of the feeder and also the problem that is known as FLISR. When there is a fault, then we have to reconfigure the system so that we minimize the customers affected. Okay? And this has to be done in real time, anytime there is a fault on the distribution system. We have to reconfigure that and so on. Okay? So I'm going to focus on the OFR problem. Okay? Basically, the optimal reconfiguration is simply we minimizing the losses. So if I look at any circuit in the distribution system, the sum of the flow, real power flow into any element is the losses. And therefore the objective function is to minimize these losses. While for the FLISR, my objective is to maximize the service or minimize the customers affected. Okay? And here is one solution. For this problem, we use the successive linear dynamic programming. And the reason is because dynamic programming is very flexible for this problem. However, the curse of dimensionality can make it really inefficient. But utilizing successive dynamic programming, where we focus on optimization around a band of the trajectory of the system over time, that generates a highly efficient problem. So you see here an example, normally in the United States, all the feeders are operated in a radial way. That is, there is always a normally open switch so that every feeder is a radial system. Okay? And of course, there are many switches with different characteristics, capabilities to open and close. And here is one solution of optimization. And notice here, this is pretty much a solution for a feeder that is an actual feeder there. Without the reconfiguration, we have losses of about 1 megawatt. With the reconfiguration, we drop to 0.4 megawatts. So that's a big change for that feeder. Okay? And I want to make the point that all of this is possible today. We are in the process of field demonstration. This is somewhere in the state of Washington. in the city of Spokane. We have here a microgrid, we have feeders and so on, and you see some pictures of the facilities, and basically we're demonstrating this process for the optimization of the feeder and the FLSR for this feeder. Okay? So these things are possible today. Okay? Now, I would like to finish with this last example, okay? And hopefully we have some time to discuss. Just a couple of months, Siemens came to me and asked the following thing, that is, we are very much interested to have an inertial meter, okay? Because we want to see how the system responds to any disturbances, what will happen to the frequency and so on. Okay? And of course, as you know, there are many approaches. The importance of frequency response is very important, especially for a system that is IBR dominant in the system, because the frequency can generate dropout of inverter-based resources, okay? If it is of a certain transient and so on, and therefore everybody is concerned with that. Okay? And we had a lot of events in the United States. As a matter of fact, these reports of what happens and so on is available publicly. If you go to NERC, you see a lot of reports of what happened. The latest was a series of events in Texas where we lost a lot of renewables because of these transients. Okay? So the experimental approach is that to go to the system and change something in the system and then measure what will be the frequency. So that will give me an idea of what is the inertia of the system. Okay? So here, for example, I can drop a load, I can drop a PV plant, a wind plant, and so on, and measure the response. Now, the problem with this approach, okay? And as a matter of fact, Siemens wanted us to do this kind of approach. Okay? And I explained to them, for my local utility, I need a disturbance of 4,000 kilowatts, megawatts, to change the frequency by 0.1 hertz. So if I make a disturbance here, let's say 100 megawatts, what I'm gonna measure in terms of frequency? Nothing. Okay, so it's not gonna be a reliable way. Okay, so here is the alternative approach. I have this system, the digital substation, where I have validated models. Okay, why can I use the validated models to tell you what is the frequency response and what's the inertia of the system? Now, for this, I need to have models, appropriate models, and the validated models are actual models, and they represent all of this, what will happen with the frequency change, what is the AGC controllers, and all of this is there. Similarly, for the inverters have controls that are continuous, and they have controls that will activate if something happens, such as the low voltage right through and so on. So there are a lot of controllers like this. Then having these models, I can do immediately a small signal frequency response and also a large scale frequency response. And I'll tell you what exactly, how exactly the system behaves. And because these models are validated and they're valid at this instant of time, I will give you the actual answer of what the inertia of the system is. Okay? And the digital substation basically provides this capability. So this project, from the time that initially we talked about doing all the experimental things and finding where we're going to do that, and as a matter of fact, we discussed about going to Rhodos and asking them if they can allow us to do that, and so on. So now it is a simple software program. Software project, and that will provide this information. And also, in addition to this kind of the experimental approach, is difficult from another point of view. Here is the recreation of an event that happened in California. That event happened in 2016, something like this, I guess, where because of these transients, about 1,300 megawatts of PV facility dropped out. Okay, and the reason was the following thing: that is, there was a fault on a 500 kV line, which cleared within the, as you can see here, within about 2.5 cycles. But during the fault, it generated a phase shift. And of course, when the fault was clear, the phase shift going back again. You can see here the results. The frequency deviated to about 89.6, and that caused the dropout of 1,300 megawatts. Now, if we have these events, and many times larger disturbances than this, then we can lose a lot more power, and therefore we have a major disaster in the system. Okay? So the application utilizing the results of a digital substation to do this analysis is a straightforward application of the digital substation. And with this, I will give you a picture of the Dipylon. For our non-Greek audience here, the Dipylon was the gate where somebody visiting Athens in the old times had to go through. And now what you see is only the foundations of this. So you have to imagine the Dipylon is set in here, I guess. And there was a big facility where they will prepare for the Pan-Athenian Games and things like that, I guess. And you have to imagine the gate there. And with this, I guess we have time to some questions.
Thank you, Sagi.
Thank you.
You took us from California to New York to ancient Greece, so thank you very much. We have time for maybe one or two questions, so anyone want to jump in? I'm sure Vasilis or Professor Gounas.
Just a clarification, Saki, very nice presentation. When you did the inertia measurement, you don't need an external event, you simulate the external event, and in this case, how are you sure that your inertia constants for the generators are the real ones? Because if you have no chance to measure them, how you know they are correct?
Okay, that's a very good question, and also opens up to give you some more information about this. First of all, the validated model includes the inertia of the generator, because basically, think about the following. If I have a relay that monitors continuously the model, there are going to be some instances where there are going to be some transients in the generator, and if I don't have the correct inertia constant for the generator and other parameters, that will flag up and will correct it. Now, the other important thing is that if I compare the experimentalist approach and the model-based approach, the frequency response of the system is location, it depends on the location of where I want to measure the inertia and where the disturbance occurs. So with the model-based approach, I can do all of this. I can apply disturbances at any points that I want to apply, and I can measure the inertia at any point along the system. So that's a bigger advantage. Well, with the experimentalist approach, these experiments are very expensive, and you're not going to do it for many points.
You don't do it as an experiment, but you have the data for a specific event, and then you do that.
Exactly.
Any other question? Yeah, Vasilis, I'm looking at you.
Thank you, Professor Meliopoulos, for the nice presentation. I would like to ask about the dynamic state estimation-based protection scheme, let's say scheme. Who is actually responsible for operating this digital protection scheme? There are too many data collected from the control center. Is there actually a need for human intervention? Let's say if a hidden failure is recognized, or is it a totally automatic system?
Great. First of all, if there is a hidden failure, the system will have time to go through has a self-healing capability. Because think about the following, that if there is a short in one instrumentation channel and the relay gets 0 for current for phase A, for example, then the dynamic state estimation for the substation can compute the best estimate for that particular current. And then it sends it back to the process bus and replaces the actual data from that instrumentation channel with the corrected values. So the system can operate normally. While we don't have this capability with the legacy protection and numerical replace and so on. And at the same time, it sends a message to an operator and say, this is happening in the system, and then some technician can go and fix it. So that's the approach. Was it there, the second question? That's it.
Great. I propose, I'm just noticing, there was a message. It was Alain? Alain, you wanna, yeah.
Yes. First, thank you for
muted.
I cannot hear you.
You hear me?
You're muted.
Okay.
Or maybe your audio.
We can hear you.
Μπορεί να χτυπήσετε το μήνυμα να... Πατήστε το μήνυμα, θα το διαβάσω.
Do you hear me?
We cannot hear you.
Can you tell us about progress made in DC current switching for the development of DC networks connecting wind farms? Progress made in DC... Πάμε πάλι λίγο. In DC current switching for the development of DC networks connecting wind farms.
Oh, for this question, that is, if we can have DC wind farms and so on. In the United States, really, we do not have any of this, but there is other parts of the country, for example, Siemens. Say again?
Probably HVDC to connect offshore wind.
Yeah, but for wind farms. Okay, that's what the question was. Okay, because the US has a lot of high voltage DC lines. Okay, that is, and the number is increasing. But in terms of HVDC for wind farms and offshore wind farms, basically we don't have any yet. Okay? However, there is a lot of research. For example, we have scaled down HVDC, the low power for offshore wind farms at the research level. And also at Georgia Tech, we did a project to see the feasibility of low frequency AC interconnections. That's a very good alternative in terms of cost versus full H voltage DC. Basically, we use synchro converters, which can lower the frequency with very simple power electronics to 1/3 of the frequency. And that increases the transfer capability of the AC lines of the system. So all of this is have been studied, and we know what we can do. However, actual implementations of these systems, there is not. On the other hand, Europe, Siemens, for example, has a product where you can get a high voltage DC for wind farms connection offshore and so on.
Great. Thank you very much, Sakis. Let's congratulate. Okay.